Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant to technology and prepare for the future. Today I would like to show you a couple more useful circuits for some projects that I want to build in the near future. I needed to test, first to find and then to test a peak detector circuit. And I found two of them on the internet. I tested them, they are good enough for me, at least the enhanced version. We have a simple version and an enhanced version, and I want to present them to you in this video along with actual results, because I've tested them on breadboard and I have made some oscilloscope screen captures and even a video capture showing in real time how these work. First of all, we will take a look at them in microcap, in simulation software, and then we will move on to the breadboard. This should be a fairly simple and a fairly quick video, because there's not much to say. The circuits are relatively easy. However, before I start, I need to make one small mention, which is the fact that I will be talking, or actually I will be just referencing a phenomenon called operational amplifier saturation. And I have talked about this in a video 2 weeks ago. I will put the link in the description. So just so you know, when I'm mentioning that particular phenomenon, I won't go into details, but if you want to learn more, just take a look at that particular video. When it comes to circuits like these that tend to be more complex, manufacturing them at home can become more difficult. Luckily, there is PCBWay, a leading PCB manufacturer with many more capabilities to help you build even your most difficult projects. You can easily get an instant quote for PCB manufacturing from the website's front page, upload the Gerber files, and have your PCBs created in just 24 hours. Need more to get your project finished? They also offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. This way you don't have to do the tedious work yourself. Or perhaps you want just the CMD stencils, so you can solder the components yourself. Just finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project, offering you a one-on-one customer service to make sure that your circuits get fabricated just the way you want. Are you building a circuit for a device that will need a case in the end? Then they can certainly help you with that as well, offering you 3D printing or injection molding services to have your custom-made plastic case, or perhaps CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com, the link is in the description. Thank you PCBWay for sponsoring this video. And now let's get started with the circuit. Alright, so we have first of all the simplest version. We need just an op-amp, a diode, and a capacitor in parallel with a resistor, although the resistor is optional. So first things first, in both cases we have circuits powered by plus minus 15 volts differential voltage, and we will have a triangle wave signal reference to the ground. I will show you in a moment. This is so that we can we are able to see more easily what's the actual maximum value, and then what is the output of the circuit that we are looking at, so that we can compare them easily. Of course, it could work with a sine wave or with a rectangle wave or a square wave, but I find it easier to work with triangle waves. So the idea is very simple. It's an op-amp that basically works like a buffer. The input signal is being fed into the non-inverting input. The inverting input takes a look at the voltage across a capacitor that's connected to the ground. Again, the input signal is also connected relative to the ground. And the idea is that when the input voltage is lower than when the voltage on the capacitor is lower than the input voltage, then the op-amp will engage, so to speak. It will polarize this diode. It will open this diode, which will charge this capacitor up to the voltage that is the input signal. When the input signal falls below the voltage on the capacitor, then the op-amp's output will tend to go down towards the negative power rail. But in this case, this diode will be reverse polarized, therefore it will be blocked and it will not allow any current to pass through it. So the capacitor will be able to just keep its stored charge theoretically in an indefinite amount of time if we would have no resistor whatsoever. If we do have a resistor, then the capacitor will start to discharge, basically depending on its capacitance value and the resistance of this resistor. The higher the capacitance and or the resistance, then the lower the speed of this discharge will be. The lower these values are, then the faster the capacitor will discharge. So basically, by playing with these two values, we can adjust the time of this peak detector. Now, this circuit works decently. However, it does have the problem of the op-amp reaching the saturation point when it will try to drag when the input signal will be below the voltage on the capacitor, because there is basically no more feedback between the output of the op-amp and inverting input. The output will be able to go down to the most negative value, and some internal transistors will go into saturation, and as a result of that, then it takes a while for those transistors to start working properly again. So the peak detection will have some dead times, so to speak. It will have some moments in time when what we have across the capacitor will not be quite accurate in accordance with the input signal. However, for simpler projects, I guess it wouldn't be a problem. So if we simulate it with the blue, we see the input waveform. Like I said, a triangle wave goes from 0 to some voltage that I can set with the slider just to make it easy for me to simulate multiple values. And with red, we see that we have the output of the circuit that tracks pretty well the maximum value that we have on the input. Now, like I said, we can play with the values of the capacitor and or the resistor, and we will see that basically we get a slower or a faster response based on these values. But because we are affected by the saturation of the op-amp, we see that sometimes the op-amp is able to react faster, like here. Okay, and some other times it will allow the output voltage to go a bit higher than it should until it actually starts to work properly. And so basically this output signal response will not be quite so smooth and quite so nice. And this will be especially visible when we have lower values here that basically make the circuit work faster. Nevertheless, it's still an interesting circuit to have in mind for some not so pretentious projects. Now, when it comes to improving this and basically preventing this op-amp from going into saturation, we basically have to use another op-amp, just like in the previous video where I showed some circuits for precision full wave rectification. We have something similar here. Basically, we have two buffers that make sure that no op-amp is going into saturation. The second op-amp is the most basic buffer. We see the output connected directly to the inverting input. So this op-amp will give exactly what it sees on the non-inverting input to the output. The first op-amp, which is equivalent to this one in the upper circuit, the first op-amp, however, works exactly like in the previous example. We see the same diode on its output that basically feeds current into a capacitor, which can have a resistor in parallel to adjust the speed of peak detection. But we also have another diode here placed like this. This diode basically prevents the op-amp to go into saturation because it won't allow the output to go lower than whatever signal, whatever voltage we have on the input signal minus the diode voltage drop. Okay, and of course we need to have another resistor from the output all the way to the inverting input, because we need to have a feedback from the output of the entire circuit, so that this buffer knows what to pass from the input towards the capacitor. And really, this is the entire circuit. Okay, this is the ground. We have here the ground, and the functioning is absolutely identical. When the input signal has a higher voltage than whatever we have on a capacitor, this buffer will drag its output upwards towards the positive power rail. It will open this diode, it will start to charge the capacitor, right? The same voltage will also go out completely on the output of the entire circuit, because again this is another buffer. And when the input signal is lower, has a lower voltage than whatever it is on the capacitor, this first buffer will drag its output down, but it won't go down further than a diode drop. This diode will be reverse polarized, just like before. It will not allow this capacitor to discharge completely, and whatever to discharge faster through the rest of the circuit. It will only discharge through this resistor if it exists. And then again, just like before, whatever voltage it has across it will be thrown to the output. So this is how we have an improved circuit, and let's simulate it to show you. Okay. Now, of course, with 10 microfarads and 1 megohm resistance, we had a pretty good working circuit before as well. However, now let's make these smaller and let me show you that it's a lot more consistent. Okay, so with 1 microfarad and 100 kilo ohm, the reset speed, let's call it like that, reset speed, is definitely higher. This is why we see with green, we see the output of the entire circuit, and it's still a triangle wave because on the positive edge the buffers work instantly, so they are able to charge the capacitor instantly. However, well, I said positive. It's not like it's on a positive edge. It's more like, you know, when the input is higher than the capacitor, it works instantly, and then the capacitor starts to discharge, and it discharges a lot quicker because of these smaller values. However, what we clearly see here is that because the op amps are not going into saturation, we have a consistent time of charge and discharge no matter where we are in this signal, okay? And we can make the input's amplitude lower or higher, but we see the same consistency across across time, basically. Okay. And I've made it a bit too big. Okay, so this is pretty much it. And now let me show you just a few results. I've set 1 microsecond per division, and on the breadboard I've left 10 microfarads with 1 megohm, which are quite a lot. It takes quite a lot of time for the peak value to come back into a lower value when the input signal changes. We have here 1 second per division, and we have almost the entire screen of the oscilloscope. Here in the left side of the screen, I have increased the input signal's amplitude quite suddenly from the signal generator, and then here around here I have decreased it suddenly up until it reached this new amplitude, just so I can see how the output voltage decreases. The output is with blue, input is with yellow, and because here I've pretty much gone out of the screen, I've repeated the experiment. Okay, my oscilloscope is one of the cheapest, so it's not able to draw correctly the input signal when I have such a long time per horizontal division. So just basically follow the blue line, because that's a lot more accurate. Okay, here I have 3 increases in amplitude, one here, and one here. We see that the peak detector output signal has jumped instantly, but then when I jumped back to a lower amplitude, it took quite a lot of time to come near what was the actual amplitude. And actually here it took more than 10 seconds to finally reach the final amplitude. So yeah, here we see something a little bit better because I've only increased the amplitude twice. Anyway, I can show you a lot better video, and you can see clearly how I start from a relatively higher amplitude and I decrease it, and then I wait, and yeah, with blue we have the output, which is the peak detection, with yellow the input. And as we can see, increasing the input increases instantly the output as well. Decreasing the input will decrease the output slowly. Again, we are playing with the time, with the speed from that capacitor and the parallel resistor with it. I've also tested this circuit with smaller amplitudes. I'm going to jump a little bit in my video. This is a pre-recorded video. So we see here at 200 millivolts input signal per division, we have about 400 millivolts peak to peak. earlier it jumped because of the signal generator that sometimes jumps to a very high amplitude for a very short amount of time, but it is enough to trigger this peak detection circuit. Okay, and now I'm further lowering the input signal to see if it works well with smaller signals as well. So we have here 50 millivolts per division, and we have plus minus 100 millivolts, and now I'm going even lower. I'm going to plus minus 50 millivolts input signal, so 100 millivolts peak to peak. Now I'm getting even smaller. At 20 millivolts per division, I have about 40 millivolts right now. And at some point I will activate averaging mode acquisition, because the noise here on the input signal is just a bit too high. So in order to see things better, here I average, I create 256 samples average, so that we see a bit better the input signal with yellow. 20 millivolts per division, we have less than 40 millivolts peak to peak, but with blue we see basically the peak detection working just fine. Yeah, so that's pretty much it. Not much to it, but it's still a useful circuit that it's good to know, because sometimes we need to use it. I will show you in a future video where I've used it, because I want to build a custom multi-channel multimeter with an Arduino board, and of course I need a front-end circuit, and that front-end circuit is a bit more complex, so I needed there to use such a peak detection circuit. I will show you in a future video how I integrated this within a greater circuit, and basically to give you a clear example where we might use it. Although it can also be used very well in audio devices, audio circuits, when we have graphic equalizers, and we have various view meters for different frequency bands. And let's say instead of seeing the instantaneous amplitude for each frequency, we may want to see the peak value. So in that case, we simply use such a circuit. Anyway, I hope you found it useful. Thanks a lot for watching. Don't forget to like and perhaps subscribe to the channel if you would like to see more of these in the future. Also, please consider supporting my work on Patreon. The faster I can buy components and lab devices, the faster I can study circuits and come here on YouTube and show them to you as well, so I can make your life easier. Once again, thanks a lot for watching this, and I will see you in the next video. Bye bye.